Harmonic functions, which are solutions to Laplace's equation, are extremely important in a lot of applications because of the relationship to the heat and the wave equation. So to kind of get us going here, I have written the Laplace equation. The Laplace equation, that's not an equation, that's just a definition, but the Laplace equation is that this is equal to 0. And I've written next to it the heat equation, which involves this Laplace operator and the first derivative, the first time derivative of the thing that we're interested in. It's not always heat, but some things can be described that way. And wave equation, c here is the velocity of the wave, and again, this applies in a lot of other situations. And so, but these both involve this Laplacian, which means that they involve harmonic functions. So it's important to try to understand about harmonic functions as much as possible. And there are some striking properties of harmonic functions that are worth exploring in a lot of detail. There's actually one striking property, but if we allow ourselves to do a bunch of algebra, we'll find that the details can help us with a lot of applications, and so that's what we end up doing. So there's really one idea and then a lot of details. So let's get on with it. The idea is that a harmonic function is kind of half of an analytic function, and so if, this is a big if u is harmonic, and it has a well-defined harmonic conjugate, so that's using the Cauchy-Riemann equations, we can have an analytic function, f is u plus iv, so v is the conjugate, which may or may not exist. And so that gives us an analytic function. So everything that we know about analytic functions can be applied to this function f, and that's what we're going to do. Now, the thing that we can get away with here, because v may not exist, but if we look at the differential of f, which would just be du plus I dv, instead of dv, we can use the conjugate differential, and that is something that automatically exists, and so we're in in a much better situation here. So I'm just going to write this as du plus I, and this is super awkward notation, star du. So star is the conjugate differential, and it's equal to dv if v is well defined, but this always happens, and dv doesn't always happen. So let's stick with the thing that we can guarantee that we get. Now, we have an analytic function, and we know Cauchy's theorem. So by Cauchy's theorem, we have that the integral over a simple closed curve gamma in a region where f is analytic, which isn't always automatic, as you've seen, of f of z dz is 0. That's Cauchy's theorem. And what we can do now is kind of split this up and say, well, that means that the integral of du over whatever that gamma is plus I times the integral of star du over that gamma. So we've just split this into real and imaginary parts. Well, this is 0, and du is exact. By definition, it's the differential of a function. That's the definition of being exact if you can write something as a differential of a function. So what you get here is that because the integral of du is 0, the integral of star du is 0. Boy, this is awkward notation. That star really messes things up, but we're stuck with it. It's been around for a lot of years. Okay. Now, we've got ourselves an analytic function, and we know things about du and star du. And one of the things that we can do with this is that V, the harmonic conjugate, is well-defined, single-valued, on simply connected regions. And that's now a consequence of Cauchy's theorem, as was just written down. So we know some places where we can use dV instead of du. There's another video where I'm talking about like this, where you have a well-defined harmonic conjugate here and here and here and here, and now this is making that more formal. Okay, so we do have harmonic conjugates, and on these simply connected regions. And now we're going to look at a specific one. We're going to look at a circle. We're not going to look at a circle. We're going to look at the unit circle, and we've got, for analytic functions, the Cauchy integral formula. So let me write that down. It should be something that appears to you often in your dreams in a good sense. So we've got that f of z sub 0, that's the unknown point, is 1 over 2 pi I times the integral from 0 to 2 pi of a fraction, f of zeta d zeta over zeta minus z0. So this is just the Cauchy representation theorem, and it's just such a useful thing. And that's great. But now we're talking about a specific circle. We don't necessarily have to make it the unit circle, but if we do make it a circle, we find out that there's a lot of stuff that happens, so that if we parametrize the circle as zeta equals z0 plus big R e to the I theta, then so that's our proposed parameterization. As long as R is small enough that we stay within some nice simply connected region, then we have d zeta. And z sub 0 is a constant in this context. And so all we're left with is IR e to the I theta. That's using the chain rule. And there it is. So what happens now is, if you apply this specific parameterization to the Cauchy representation formula, what you end up with is 1 over 2 pi. In the representation formula, there's an I, but now when we do the change of variables, there's an I on top, so those are just going to cancel. And there's an R on top and an R on the bottom. Zeta minus z0 is R. z0 is the center of a circle of radius R. So there's an R on top and an R on the bottom, and we end up with this very simple expression saying that's the integral, the integral from 0 to 2 pi of f of zeta d zeta. So zeta is the variable on the circle, and that is f of z sub 0, f of the center of the circle. You get the value at the center of the circle by integrating all around the circle. And it's called a mean value property, and that's right. It's, if you integrate around the circle, then you get the mean value. The average value is what you called it in Calculus 1. And so this is now the Cauchy representation formula. And now we have a nice surprise. We just take the real part, and if we take the real part, and remember what we have said, I'll outline it up here, is that we've said we started with the harmonic function u, and we souped it up to being an analytic function, u plus iv, using the harmonic conjugate. And in a situation like this, the harmonic conjugate exists. And if we take the real part, now we find that u of z sub 0 is the integral, there's a 1 over 2 pi. I'm sure there's a 1 over 2 pi. 1 over 2 pi, integral from 0 to 2 pi of u of z sub 0 plus r e to the I theta, that's a capital R, d theta. So this complicated looking formula is really just the Cauchy representation theorem. We've taken the real part and we've done it in a very specific context so that we can actually evaluate some stuff. We can actually do the algebra. Now comes a trick. And the trick is this. It's called the Riemann mapping theorem, which we have not studied yet. And it's a deep theorem. So I'm just going to say it's a fact, Jack, that if you have any simply connected region, it can be mapped conformally into the unit disk. And that's great. So that now makes this applicable to any simply connected region. We haven't proven the Riemann mapping theorem, but it's been proven. And so we can soup this up to use it on much more complicated regions as long as they're simply connected. But we want to do a specific one. So the specific one we want to look at is has this explicit formula. We're going to have zeta is a fraction. It's a fractional linear transformation, so it's a fraction. And the top is r times a factor, r being the radius of the circle that we're trying to work with. And that factor is z minus a. So when you put z equals a in here, then that goes to 0. And the bottom is r squared minus a bar z. Okay, so that's very explicit. And having that being explicit means that we can start to look at some of the derivatives and the like. The more general Riemann mapping theorem, you may not have anything so explicit, but here you do. Now, the situation here is people aren't always so good about explaining this, and I'm not sure I can be much better. But when we look at the parametrization of a circle, the center doesn't matter. You've got r times e to the I angle. And when you take the derivative of that, you get I times r times e to the I angle. So there's this situation where you're not getting at the angle, you're getting at this extra factor of zeta. So what you really want is to say, and I'm going to put this in quotes because it's a little bit on the flaky side, is we're going to say that d theta is, it looks like a fraction, it's got a top and a bottom, is d zeta over zeta. This is tied up again with the conjugate differential, and it's written like this in L4s. And this is really equal to, not in quotes, the differential of the log of zeta. Well, that's just pretty neat and keen because this, using the quotient rule, is kind of a pain, but if we take the log, the derivative comes out quite nicely. And I'm going to shortcut this because calculus is a prerequisite. And what we end up with is, and this is also done very explicitly in L4s, and so what we end up with is the following. Applying this transformation that takes the arbitrary circle to the unit circle, we end up with d zeta over zeta is this fraction. I'm sorry, so that's d of log zeta. This fraction, it's pretty simple algebra. The top is r squared minus the absolute value of a squared. And the bottom is absolute value of z minus a squared. Now, a is something in the interior that's getting mapped to 0 in the unit circle. And so z is never equal to a. Z is on the circumference of the circle, and a is the center. So we don't have to worry about the bottom of this fraction being 0. And we'll just call that d theta. So there's what happens when you do the logarithmic derivative. Remember, I'm scanning this, so you don't have to try to copy it down right now. And so this leads to the Poisson Integral Formula, which is saying that you can find the value anywhere in a disk of a harmonic function by integrating around, not just at the center, but anywhere by integrating around the perimeter, the circumference, and then the adjustment is made by this fractional linear transformation. And so that gives us the Poisson integral formula. And so that's written very explicitly in Alfors. It's on page, these pages are hard to read, sorry, page 167. And so that gives you the Poisson integral formula. It's in there, and I won't write it down. And I'm also not going to write down, because it's in there in Alfors, the polar coordinate version. And the polar coordinate version is, it's kind of fun to write down, but it's a little bit of a mess. And so I'm going to leave it to Alfors. You can look it up in Alfors to see what it is. But it's a big old nasty fraction. You've got the distance of A from the center as little r, and the radius of the circle is big R, and you're looking at the difference of their squares on top of this fraction, and something that kind of looks like the square of their differences to their squares, but it takes into account the angle. As you're going around the circle, you've got theta, but this point A is at some specific angle. Excuse me, we're doing complex analysis. The argument is phi. And so the difference between those, actually the cosine of the difference between those, is what modulates this not square, but it looks like it could be a square on the bottom of the Poisson integral formula. What you need to do is compare the Poisson integral formula to the Cauchy representation formula. The Cauchy formula is a lot easier, and so that's why so much progress was made in fluid dynamics because that involves harmonic functions. So much progress was made with fluid dynamics by switching to the complex case and using the Cauchy integral formula. So this is what happens without the Cauchy integral formula, and then we can compare it with the Cauchy integral formula. These problems are much easier to solve in 2 dimensions because we can pass to the complex case, or as someone said, and I can never remember who it was, the shortest path between any 2 points in the real domain passes through the complex domain.